Good morning, everybody. Now let us start experiment number 8, which is a simulation-based experiment. So far, we have seen 7 programs, which will be programming in MATLAB. Experiment 8 and 9 will be simulation, one in Simulink, the other one in other supportive add-on toolbox. So experiment number 8 is load flow analysis using Gauss-Seidel Newton-Raphson method and fast decoupled load flow method for both PV and PQ buses. So initially, before going into the experiment, we'll be using a toolbox called as PSAT, PSAT Power System Analysis Toolbox is abbreviated as PSAT in MATLAB. So let us see how to start or invoke with this PSAT, and then finally we'll continue with the experiment implementation using PSAT. So once you open MATLAB window, in MATLAB command window, just key in PSAT. Once PSAT is installed in this particular system, if PSAT is typed in command window, the following screen appears. Whatever I am showing here, it gives PSAT. It is an open source toolbox, followed by the next screenshot that you can see here. It will show the version PSAT 2.1.8 along with this interface window. Then in this interface window, we will have to go for PSAT Simulink library on the menu. So on the menu, we have an icon here that I am displaying. Here I am showing using the mouse. This is Open PSAT Simulink library. You will have to select this Open PSAT Simulink library. Then once this library opens, this is the library folder that you can see over here, and sometimes it is required to unlock the library, which has to be done, and this is the preview or screenshot of the library folders. Then over here we'll have to select file. After clicking on file, click on new model. So once you click on new model, the following screen appears. In the screenshot number 4, you can see that the following blank window opens. This PSAT add-on toolbox is basically compatible with Simulink of MATLAB. So it's called as model file. All MDL extension files come under Simulink. So we will be creating the model or circuit over here in this window, followed by analysis using PSAT. Then in step number 5, let us go for the implementation of the example for running the load flow analysis programs. So coming to example number 1, please have a look at this example. This is a 3-bus power system network. In this 3-bus power system network, each of the 3 lines has series impedance of 0.02 plus j0.08 per unit, and the total shunt admittance of the lines is j0.02 per unit. The specified quantities at the buses are given below. That is, the bus data is given over here. Bus 1, bus 2 and bus 3. The real load demand PD, reactive load demand QD, real power generation PG, reactive power generation QG. At the same time, the voltage specification is mentioned in this particular table. Already we have solved this problem theoretically in the class. Same thing we are implementing right now using the software. So step 1, you'll have to drag and drop all these components onto the new model from the library. First one, this is the symbol for slack bus. This is the symbol for bus. Third one is for PV bus. Fourth one is for transmission line pi model. Then we have PQ bus. Then this represents the load. The last icon represents the load. So you will have to drag all these symbols from the library onto the simulation screen where you are going to design the circuit. Then please have a look at the given power system network and build the circuit accordingly. We just have to connect them. So we very well know that from this network, bus 1 is basically given as slack bus in this problem. So you're going to connect slack bus over here to bus 1, and here you can see 2 plus J1 as load on bus 1. So I'm going to connect the load symbol over here. Then coming to bus 2, they have shown 0 plus J0 as load, so there is no load at all. and there is a generator that is shown which is zero point 0.5 plus J1. So basically this is a PQ generator. See, in the software they have segregated PV generator and PQ generator depending upon nature of bus. So bus 2 is basically PQ generator. So you have to connect PQ generator to bus 2. And coming to bus number 3, we are having load as well as a generator that is shown here. But this happens to be a PV bus as per the data. So you will be connecting PV generator and you will be connecting the load. So first and foremost step is to drag and drop these components, that is slack bus, bus 1, PV bus, transmission line, PQ bus and load. In step 2, you are going to connect them as per the given power system network. Next, we'll move on to step 3 where we try to input all the parameters. So first we'll input the parameter for slack bus. So for slack bus, basically, if you have a look at the problem here, for the slack bus, the following information is given. See, in case of slack bus voltage is 1.04 plus J0 and PD and QD are 2 and 1. So we'll have to input the same. Here, for slack bus, we have power and voltage ratings. So you'll have to double click on slack bus icon. This screen will be displayed. Over here you'll have to enter MVA as 100, which is base MVA. 400 kV is the base kV that we are going to use throughout the network. And given voltage magnitude is 1.04. Then if you observe the network, at bus 1 we are also having a PQ load. Double click on that PQ load, enter these parameters. Again, base MVA remains the same, which is 100, kV is 400. Now real and reactive powers are 2 per unit and 1 per unit. It is given as 2 plus J1 in the network. Next, similarly we come to bus number 2, double click on that PQ. Here again we are going to enter power and voltage ratings. Active and reactive power generated are 0.5 and 1. So let us have a look at the network. So in this given problem, you can see that at bus 2, you are having generator which is 0.5 plus J1. So same values have been entered. So over here, PQ generator at bus 2, you have 0.5 and 1. Next, going to bus number 3. So coming to bus number 3, here we have PD and QD as 1.5 and 0.6 and QG is unknown, which has to be found in the solution. V3, voltage at bus 3 is 1.04. So let us see, we'll have to enter 1.04, 1.5 and 0.6 as PD and QD. So here PQ at bus 3 as usual, 100 and 400 base values, 1.5 is the active power, 0.6 is the reactive power. Then we'll have to input the details for transmission line. Double click on the transmission line. As usual, base MVA 100, kV is 400, frequency is 50 hertz. And here resistance and reactance of the line in the problem is given as 0.02 and 0.08 as reactance. Susceptance, that is nothing but shunt admittance, data is given as 0.02. We do enter all these parameters. So after entering all the parameters, save the file, give some name for the file, and it will be in .mdl extension. Save it with .mdl extension. Then go back to the PSAT main window that I had shown in the last in the starting screen. Over there, double click on the data file. So once you double click on the data file, whatever file you have saved here in the previous step will appear in that list. Select that particular file and click on load. And then in the PSAT window, under settings, select power flow solver. And here you can select either Gauss-Seidel method or NR method as per your preference. So in this particular experiment, we'll be doing both Gauss-Seidel and Newton-Raphson. First you will go for Newton-Raphson, then you will go for Gauss-Seidel. Then click on power flow in PSAT window. Let me just show you the same on the screenshot over here. Yeah, this is the window where you'll be configuring the settings. This is power flow. If you click on power flow, the activity is going to start. So then you'll be selecting Newton Raphson in that settings. And then once this process is completed, you have a provision to select static report in the PSAT window. You'll be selecting click on report, and then you'll be selecting the output file. And here this shows your output file or the result. It will show you the power flow results, bus 1, bus 2 and bus 3, what are the corresponding voltages, magnitude and angle, then power generation, reactive power generation, active and reactive power load information it will show you. Then over here, line flows, that is nothing but active and reactive power flowing in the transmission line will be indicated. Transmission line between bus 1 and bus 2, bus 2 and bus 3, and bus 1 and bus 3 will be displayed here in per unit. When you are selecting the report itself, you can either select per unit or actual values. Depending on that, the results will be shown. And then you go for line flows from bus 2 to bus 1, that is the power flowing in the other direction also will be displayed. Then you have the global summary report, which will talk about total generation, total demand and total losses. So whether your analysis is right or not, you can also cross check here by verifying the power balance equation, which says total generation should be equal to total demand plus losses. So here you can check the total real power generation is 3.5316, the total load is 3.5, and the real power loss is 0.03. So if you add up 3.5 plus 0.03156, you get 3.5316. Similarly, in case of reactive power also, you just have to add 1.6 plus 0.05958, that will give you 1.6596. So total generation is equal to total load plus losses. Separately you have to check for real and reactive. So this completes the 8th experiment. You can take one more additional example as shown here in this manual. I have given one more example with a different data. Same process has to be followed, and you'll have to check for the results. Here also we can see in this particular problem, results I have taken in actual units, megawatt, MVAR and all. So you can check for the same. So this completes experiment number 8.